Okay, this is for physics 1180, college physics 1, and we're going to talk about work and energy. Okay, so let's talk about gravitational potential energy. And we're going to talk about two different types of potential energy. We're going to talk about gravitational and then also elastic. Let's first start with gravitation. Gravitational potential energy is equal to the mass g times 10 to the h. Now you notice there's a negative here. This negative only means when you are comparing it to kinetic energy in a system. Okay, normally that doesn't have to be there, so we can just take that out, but sometimes it's going to be there depending on the physics of the problem, and then we're going to talk about that too a little bit. Gravitational potential energy is in a conservative system, and this is important, in a conservative system is equal to the work done to raise a mass a certain height without air friction. So we're not going to take in consideration any of these problems with air friction. So potential energy is equal to mgh, or it's basically equal to the force, the initial force, times the height it goes. So potential energy is also equal to the work done. This is in a conservative system. So I'll put down a C for conservative. Okay. And so we also can say that the work energy theorem is equal to mg, the potential energy, of the change from the initial height to the final height, whatever that is, whatever the problem will dictate when we work out a problem. There's no such thing as negative energy. The negative may mean lost energy to the system. Be careful with the negatives, okay? A lot of times a negative will mean that the energy is decreasing, where a positive may mean the energy is increasing or standing still. Okay, so let's look at an example in potential energy. A boy throws a ball up 10 meters when the ball reaches its highest point and the vertical upward velocity is 0. So at that point, what is the ball's potential energy? At that point, if the mass of the ball is 0.2 kilograms. So, as you know from projectile motion, a ball is thrown up with a certain velocity and it comes back down, okay? The vertical velocity here is always z, or 0. So we always have 0 right here. This is the vertical. I'll put a y there, okay? So where v equals 0, P, E, M, G, H, delta H, and plugging in the numbers, we have 19.6 joules. Now, this is the potential energy when the ball is at the highest point. Let's look at another example in a conservative system. Calculate the potential energy of a 50 kilogram mass at 100 meters. The mass falls. Calculate the speed at the ground. Okay, so here's our potential energy equation. We first want to know, since it's a conservative system, how much energy is in the system. And we have about 49,000 joules. The work energy theorem, we could set that to 49,000 joules. And since the initial velocity is equal to 0, then this goes to 0 right here in this equation. And we can now solve for V of F. And we do 2 times the work. We know that what the work is. We figured it out right here, divided by the mass. And we have a velocity of 44.3 meters per second. So the ball falls when it hits the ground at 44.3 meters per second. So this is at the ground. Okay. Let's look at something on an angle, which is on a slope. We have a slope, and an 80 kilogram block slides down the slope at 30 degrees, 100 meters to the bottom. So we're given a displacement that is parallel with the slope. What is the potential energy? Okay, so the first thing we need to do, we know we have a triangle here, and this distance is the hypotenuse. So we can set up sine 30 degrees is equal to delta H, which is in the y, and delta D, which is the hypotenuse. And this way we have a equation that we can use later on to figure out this problem. So delta H is going to be equal to 50 meters. So we have 100 meters down the slope, and we have a height of 50 meters. Potential energy is then going to be equal to the mass times the acceleration of gravity times 50 meters. And we only need to worry about the height in potential energy, gravitational potential energy. That's all we're concerned about, and we find we have 3.92 times 10 joules. So remember, potential energy, this box is standing still, and it has this potential energy right here. Okay, we're going to stop right here, and part 2 will take up the conservation of energy.